Find a degree 5 poly with a lead coefficient of 1, roots of multiplicity 2 at 3 and 0, and another root of multiplicity 1 at negative 5. So our function, our basic starting point, is going to be a times our intercepts. Okay, so we're going to take this piece of information, roots of multiplicity 2 at these locations. So maybe what we could do at sort of simultaneously is come up with the graph. So x and y. So at x equals 3, 1, 2, 3, we have an x-intercept, and it is even multiplicity. And at the point 0, we have an x-intercept that is even multiplicity, which means those are bounce backs. And then at negative 5, 1, 2, 3, 4, 5, negative 5, we have another x-intercept that is odd multiplicity, multiplicity of 1. And so just graphically, kind of understanding what we're doing. So the yellow portion here is going to give us this information. So now if we do some simplifying, and they do tell us we have a coefficient of 1. So we know that a is 1. So f of x equals 1 times x minus 3 squared times x squared times x plus 5. First thing, x-intercepts, negative 2, 0, and 1. And then you take that information and you interpret it as x plus 2, x minus 0, x minus 1. The second layer is multiplicity. So go through each x-intercept and determine its multiplicity. So for the negative 2, looking at the graph, and your focus is on this guy right here. For the negative 2, what is that multiplicity? Probably a 1, right? So we're gonna put a 1 right here. Look at the 0. So now your focus goes to the 0, and what is the multiplicity on the 0? Probably a 2. We know it's even, so we're going to go with 2. Okay, and then you go to the third one, which is this x-intercept. And again, you say, what's the multiplicity? You know it's something odd. And since we're playing with nice numbers, we're going to assume that it's a 1. So you put a 1 on there. Okay, so the first layer is just identify your x-intercepts. The second layer is go through and look at the multiplicity. Right here, they tell you that your coefficient is either plus 1, so a is equal to either plus 1 or a is equal to negative 1. Before we can go further, let's simplify our function, because there is some simplifying we can do. So we'll say this is x plus 2. And this part here, x minus 0, well, that's just x, right? And so we'll just write x squared, so that's kind of nice. And then we've got an x minus 1 right here. Find what the y-intercept is. And if the y-intercept is positive, then you know it behaves a certain way. And if the y-intercept is negative, you know it behaves another way. What's its y-intercept? It's 0. And so that doesn't tell us whether it's above or below, because it's 0, right? It's in the middle. It's on the fence. So what we need to do is pick another point. We need to pick another test point and see what value we get and see if it matches the graph. 1's not going to work because 1 is a 0 as well. So this point's not going to work, this point's not going to work, but this point will work. This is negative 1, positive 2. So we're going to find f of negative 1. So you're going to get a times, this is 1 minus 1 minus 2. Well, the 1 and the negative 1 cancel, and so this is just going to become a negative 2. So what you end up with is 2 equals negative 2 times a. A has got to equal negative 1. So that means our final answer, when we put this all together up here, is going to be negative 1 times, and we could actually just use this function here. X plus 2, x squared, and x minus 1. Again, we have a function that's in prefactored format. Very nice. You can rattle off the x-intercepts pretty easy. But instead of saying equal to 0, we want to know where this is greater than or equal to 0. So we're going to create the graph, and then we're just going to interpret the results from the graph. So here's our graph. Y-axis and x-axis. So where are the x-intercepts? How about 6, 9, and -2? You then take a look at multiplicity. And all of these are multiplicity of 1. So they're all pass-throughs. Okay? Great. Now we got to find the y-intercept. So all we're going to do is find f of 0. So it's a big positive number. And we're going to plot right here on the y-axis, big positive number. It's nice to know that numerical thing, but we don't really need the number. We just want to know, is it above or is it below? So now we can start sketching the graph. Starting at the y-intercept, which we know is a big positive number, we know that the function goes down this way, passes through 6, curls back up, and passes through 9. That's moving to the right. Moving to the left, we know that the function passes through -2 and continues downward. So this means that the graph is negative, 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 positive, 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 positive. And again, we're referencing the y values here. Negative, 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 positive, positive, positive. And so when we go back and look at the original idea, we want to know, where is this function greater than or equal to 0? So I think it's going to be greater than or equal to 0 along this domain, all these guys, and along this domain, all this stuff. That's where the function is above sea level. And so how would you write this as an interval? And be careful with the interval. Make sure it's greater than or equal to. Y is equal to 0 at the x-intercepts. So we're going to go hard bracket, -2, comma 6, hard bracket, union with, hard bracket, 9, comma, infinity, parenthesis. I like your question because you said, what would happen if? I love what would happen if questions. So your question is basically, what if we had another x-intercept here and this function went back up? So the first thing, all kinds of things happen now. The first thing that would happen is whatever this x-intercept is, you now have to add that term here. So there'd be like maybe an x plus 8 right there. So that's the first thing that would happen, is you would have another term in your train of x-intercepts. The other thing that would happen is these are now all positive values. And so your interval would have to then include negative infinity all the way, let's just call this 8, -8 if that's okay, all the way up to -8. So here's an idea. Let's take this stuff and color it blue. And let's color this blue. And let's color this green. Let's color this green. And let's go with your what if. And so let's leave -8 as an answer. Okay, so we'll color this green. We're going to we need to have some fish in there. So we'll put some fish in here, and then there's fish in here. There's trees. So this is you, right? And when we say, where is the function greater than 0, we mean, where is it above sea level? Where are you walking on land? Get it? So you're walking on land here, and you're walking on land here, and you're walking on land over here, and you're walking on land over here, right? That's what they mean when they say, where is it greater than or equal to 0? We need to identify, if you think about it like coordinates, like GPS coordinates. What are the GPS coordinates where you're walking on land? So I need the one-dimensional GPS coordinates where you're walking on land. And that is going to be here to here, and here to here, and here to here. If we change this, instead of greater than or equal to 0, if we say less than 0, now we want to know where do you need scuba gear, right? And so you do a little like this. And so now you're down here. What GPS coordinates would you be underwater? Where would you be below sea level? Now math makes this much more difficult because they say x is greater than or equal to 0. And immediately your brain's like, blah. Greater than or equal, what does that mean? I forget greater than or equal. But if you think about it in terms of, what does this really mean? This is a math way of saying positive numbers. And positive numbers means above the x-axis. So I just interpret that to mean above sea level. It's sea level is 0, assume that's 0 altitude. So above sea level means you're above it. So that's why the gap between 6 and 9 is not included, because it's below sea level. It's where you're less than 0. You're below sea level. Your altitude would be negative. So another problem. Solve the polynomial inequality, blah, 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 greater than 0. Layer 1, identify the x-intercepts. It looks like 11, -7, and 4. The -7 is odd multiplicity, the 4 is even multiplicity, and the 11 is odd. Now we got to figure out where's the y-intercept. So we're going to say f of 0, and we're going to get -11 times 7 times -4 squared. I'm just going to write big negative number. Okay, so here it is. We're plotting big negative number. The number is not really important. It's the sign that's important. We just need to know, is our y-intercept above the x-axis or below the x-axis? Because that provides us a starting point. So let's begin by starting at our y-intercept. That's where we like to start. And let's again go to the right. So our function's going to approach 4, and it's not going to pass through. It's going to bounce back. Then it's going to curl back and go through 11. And then going to the left, it's going to pass through -7 and continue on. And now we go back to, what are we looking for? We're looking for where this is greater than 0. And be careful, it's where it's greater than, not greater than or equal to. So that means in our interval notation, we have to use parentheses rather than the hard brackets. So where is this greater than 0? Where are you walking on land? -infinity to -7 with the parenthesis. Union with 11 to infinity. Insert screen clipping, and I'm going to grab this guy. There it is! Ta-da! Look at that. All right, so hooray for one note. The earlier question was, if you have a multiplicity that's odd. We talked about odd multiplicity, and that the idea that it's a pass-through, right? So you got to pass through like this. Well, how do we know if this is x to the first, or x to the third, or x to the fifth? Like, how do you know which one it is? And so, if you take a look at these two x-intercepts, if you zoom in on this guy, and you zoom in on this guy, okay? If you zoom in on this one, as you zoom in, this looks like a linear type thing. It looks like a line. And a line is x to the first power, right? Y equals mx plus b. It's x to the first power. Now, if you look at the second one here, this is also a pass-through. You see, it still passes through that intercept. However, if you zoom in on it, it doesn't look like a line. Instead, it looks like an x to the third power, which is something like this. And so that's how you kind of know, by looking at these graphs, whether something is to the first power or to the third power, is how it behaves as you get closer and closer to that intercept. We're not going to give you things that are to the 5th power or 7th power, but if we did, they would probably get real close, and they may do just like a little dance, kind of like zip, 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 and then go through. You're not going to see that, but this would be like maybe for the 5th power. It depends on how many wiggles it has. Remember, for every power, x to the fifth, this wiggles 5 times. 1, 2, 3, 4, 5. Something to the second power wiggles twice. 1, 2. We call this the degree of the polynomial. This guy here, if you were to write this is going to be x plus 1 to the third. That's that guy. And this one is going to be x minus 2 to the first.